Okay, we were discussing different examples of single qubit channels, right? And this is the last of them that I want to discuss because it's a bit different from the other so-called Pauli channels that I mentioned. So we are continuing our discussion of single qubit channels. You may wonder why I'm calling this single qubit and not just qubit channels, but we'll see that when we start doing error correction next week. So this was the final example that I was mentioning yesterday, and I didn't have time to complete the discussion, so I just thought I'll revisit this today. This is the so-called amplitude damping channel, and the name comes from the fact that in a physical scenario, this arises in the following context, where you have essentially a two-level system, where this is, like I said, the ground state of a quantum system, and there is the excited state. The ground state is what we associate with the ket0 typically, and the excited state is ket1. Then there is always some probability of dissipation of energy. So this is a photon, let's say, it emits a photon. And this describes a kind of dissipative or lossy process. So this is very common in physical systems, and that's why this noise model, although it looks much more complex than the more simple bit flip or phase flip kind of noise, where you could just take two unitary operators. You took the X operator and said with some probability it's X or identity. With some probability it is Z or identity. But this is no longer the case, right? There is no identity out here. There is only E0 and E1. So these are your Krauss operators or noise operators. And among these two, you can see that it is the E1 which is more catastrophic, and that is the one which actually describes this process, right? Where the excited state actually just decays to the ground state. So this is the one which maps the ket1 to the ket0 while doing nothing to the ket0, right? But what is the need for the first operator? Well, if this first operator didn't exist, we wouldn't have a representation of this map physically, right? Because we need a process finally which is trace preserving or trace non-increasing and all that, right? Just an E1 operator would not suffice to make it a physical operation. So to describe the physical operation, we need the E0 also. And what the E0 does is the following. So suppose I think of this as some, what is often called a two-level atom. And these kind of objects typically sit inside a cavity, right? So it's a two-level atom inside a cavity. And this two-level atom, so let's say I am the observer who's observing outside this cavity. So if the dissipation has happened, then I see a photon, right? And this happens, so this dissipation happens with probability P. So the P here denotes the probability of the ket1 to decay to ket0 while emitting a photon. And if I do not observe a photon, then that also gives me some information, right? So you see, whenever I have a quantum system like this and there is some leakage of information that has happened. So the photon coming out in some sense describes a certain leakage, right? And whenever that leakage of information has happened, then there has to be associated with it some disturbance of the system, right? And the way to think about what the first operator is doing is describing that scenario where you did not observe a photon. And if you did not observe a photon, then it is much more likely that the state, so in some sense, that has damped for you the probability of the ket1, right? Because it's much more likely that your state was actually in ket0. So the 1 minus p term is a kind of, you can think of this as sort of damping the probability of the, so damping the amplitude or the probability associated with the ket1, right? Because what does the first term do? The first term again does nothing to 0, and 1 is mapped to something square root 1 minus p ket1. So if you imagine that you were in a superposition, then the coefficient of your one term is getting damped, right? So hence the term amplitude damping. That is one way to understand this. And this p term here, I've written this here, can actually now go from 0 to 1, unlike in the other cases where we said p goes from 0 to a half, right? That describes the most noisy scenario. In this case, because of this, the nature of this map, so first of all, let's note a few things which are different from this map. So this is not a what I would call a Pauli channel, okay? And this is because none of the Krauss operators are proportional to Pauli's. So none of them are scaled versions of Pauli's, right? There is no term which says, which is like some alpha times X or beta times Y or anything like that, right? So none of the individual Krauss operators themselves are proportional to Pauli. The second thing you note is that there is no identity term in the Krauss representation, right? So there is no term proportional to identity. So what this means is if I act this amplitude damping on some state rho, there is no part which is simply rho plus something. If you notice all the previous channels like bitflip and so on, there was always with some probability you had a rho, and then there were order p terms, right, which had something else, which had a corrupted version of rho, right? This does not happen in this case. There is no term which is proportional to rho. Oops. On the other hand, what you now have is E0, which is not identity, and you have to write E0 dagger now. Well, E0 is diagonal, so it doesn't matter, but E1 actually is not a diagonal or a Hermitian operator, so you have to write it out with the dagger. And what is more, when I act this on the maximally mixed state, I do not get back the maximally mixed state. So this is unlike, again, the case of all the Pauli channels that we discussed so far, whether it was with flip or phase flip or depolarizing. So unlike these Pauli channels, you no longer have a term which is proportional to identity in the Krauss representation. And therefore, if I plug in identity here, you see that I'm going to get here E0, E0 dagger, which is not identity, right? It is actually 1, 0, 0, 1 minus P. That's what you'll get if you do E0, E0 dagger, right? So you don't have a term which is proportional to identity. And therefore, unlike these cases, this is not a unital channel. It does not preserve identity. It does not preserve the maximally mixed state. Okay, so this is one of the important non-unital channels that one often encounters in quantum computing. And so this, then you will see, will have some interesting consequences when you try to do error correction and all that. There is something which is a bit different about this channel. What was the next thing I wanted to? The next thing was about the fixed point, therefore. Yeah. So now you see, if I have a unital channel, then it is clear that there is already one fixed point, right? So for all unital channels, what is the fixed point that we already have?
I by 2.
I by 2. The maximally mixed state usually, I mean, it's already a fixed point, right? The maximally mixed state is a fixed point for all unital channels, but in this case, it is not a fixed point. In fact, the fixed point of the map in this case is a pure state. And which is the state? So let's work this out. So if I say amplitude damping channel acting on 0, 0, what happens? So I have E0, 0, 0, E0 dagger plus E1, 0, 0, E1 dagger. Now you see the 0 state is essentially in the null space of the E1 operator, right? Because E1 has no 0, 0 element to it, right? This is the 0, 0 element, that is 0. All other entries are 0. The only term that is non-zero is the term that looks like this, which takes the 1 and maps it to a 0, right? This is the only term that is surviving in this matrix, right? So, and this is what it represents. The 1 getting mapped to 0 is what it represents, right? So, essentially the second term goes away here. This is 0. And this, you see, the 0, 0 entry is just 1. So what do you get here? What is the action of the amplitude damping channel on the 0 state?
It leaves it unaffected.
Correct. So it's just 0, 0. Good. What about 1, 1? What do you get?
E1, 1.
And there's a second term.
That 1, 1 will not be affected.
It will unaffected again.
Yeah.
P times
This
0,
doesn't
0.
make sense, no? Sorry?
P times 0, 0.
Exactly. You need that to make this a valid density operator at the output, right? Otherwise, you just have a 1 minus P sitting there. So this second part actually works like a one-way bit flip channel, right? In the sense, I mean, the second part, I mean, the action on the Ket1, this is like a asymmetric bit flip channel, right? So just this part alone. Because whenever you have a 1, there is a certain probability for it to get flipped to 0. That's what this is saying. But when you have a 0, nothing happens. It is left invariant. And that is why I said this model is actually more physical than a bit flip model, right? Those of you who do experiments, or, if you're coming from a physics kind of perspective, you will wonder how can something like bit flip actually be physical, that it's symmetric for an excited state to jump to the ground state and the ground state to go up to the excited. That's a much more rare situation. There are specific qubit kind architectures where that may happen, but what is more natural is actually this process, right? So this then, so you can already see that out here you already have the fixed point, right? Because you have a state that is left invariant, and that state is nothing but Ket 0. So that is the fixed point of the map. So now how does this look? If I were to draw this flow kind of picture of on the block sphere, then you see that eventually somehow all of them all the states actually converge to the Ket 0 state here, right? So what happens at intermediate stages is you do get so you get these kind of actually at some point these start becoming disks, right? You do get ellipsoids, but then these ellipsoids then shrink further and you start actually getting disks around the Ket 0, and finally it all just shrinks to Ket 0, right? So it's a very asymmetric sort of shrinkage of the block sphere, where the z-axis has a preferential role, and over and above that there's a particular state on the z-axis which has a preferential role, and that state is your fixed point. Unlike in the other cases where either you had a state which is at the center of the block sphere to be a fixed point, that is the case with the depolarizing channel, or you had an entire axis which was a fixed point like the X, Y, Z, phase flip, bit flip channels. Here's very different sort of behavior, right? And finally, what I wanted to talk about was this probability and the time, right? So this P, in this case, actually, you can simply write it as 1 minus T by capital T, and this capital T is what is called a T1 time. So this entire process is often called a T1 process, okay? And this characteristic time is called the T1 coherence time or decoherence time. And you will often find for superconducting qubits or ion trap qubits, people will describe two coherence times. They will describe the T1 time and the T2 time. The T2 time is associated with the phase flip channel, as I mentioned yesterday. And it is typically a sort of toss up as to which of these processes actually is more dominant. And that depends on this characteristic time scale at the end of the day, right? So this is to also tell you that in the quantum setting, first of all, we saw several examples of noise channels. Unlike in the classical case, where if you do a course on classical error correction or what is called here error control coding, you're not going to sit and discuss noise models ad nauseum the way we have done. But that's because there isn't much to discuss. There is a bit flip, well, and there is an erasure, and that's about it. You don't have these kind of processes arising from these complex physical models which cause this very non-trivial sort of behavior. So in quantum architectures, it's often useful to think about what is the dominant noise process of that model, how does it arise physically, and that sort of tells you also about how robust your qubit is. So the values of this T1 and T2 tell you how robust that particular qubit is or that particular set of qubits are. Okay. And you see in this case, actually the flow on the Bloch sphere, again, this is homework for you. I will simply tell you what happens. You have Rx, Ry, Rz, and what happens is Rx and Ry simply pick up a 1 minus square root P, but Rz actually picks up a P plus Rz square root 1 minus P, and that's what makes this shrinkage somewhat non-trivial on the Bloch sphere. And so you eventually, as P tends to 1, in the T tends to infinity limit, your Rx, Ry, Rz has actually tended to 0, 0, 1. And this is nothing but the state 0, 0, right? Which is the fixed point on the of this map. Okay, so I think this concludes the discussion of the qubit channels that I wanted to talk about. So I want to move on to the next idea. Before that, yesterday there was a question towards the end of the class, or maybe sometime when I was discussing this about are we to understand that this map is being acted successively on the state when I talk about this flow and all that. So I just want to mention one word here. There may be some of you who have done a dynamical systems course or who are doing a dynamical systems course, I don't know. But this very much is in the spirit of dynamical maps, as is discussed, let's say, in a complex systems course or a dynamical systems course, right? And mathematically, these are what are called semi-groups. Okay, so for those of you who are more inclined towards like functional analysis or mathematics, these are what are called semi-groups. And the idea is very similar in some sense to the unitary evolution idea, where you say that if I have evolved from T0 to T1, and then I evolve from T1 to T2, then this product of unitaries simply gives me the evolution from T0 to T2, right? You have this kind of a structure when you talk about unitary evolution. In a similar way, with the CPTP maps or these noise channels, suppose I were to associate a time with this, and I think I put this at the top, right? So if I think of E T T0, T1, and this is now rho at time T0, right? Then I have to compose it, not product, right? So when the unitary is simply a single operator. So this is just a product of operators. But now when I'm applying this map in sequence, I have to think about composing the map. What am I composing? I'm composing two maps which are identical. So if it's amplitude damping, then it's amplitude damping from time T0 to T1, composed with amplitude damping time T1 to T2, right? And so on and so forth. So this operation is now this is a composition of two maps. And if I stop with this, this is going to give me the state at time T2. So when I talk about a flow in the block sphere and there's a continuous time parameterization of these maps via this P, right? This parameter P, the noise parameter P, right? This is what gives me the continuous time parameterization of these maps. Then this is how I am to understand the time evolution via a composition of a sequence of maps. And this property that I can do this in sequence and get the state is called a semi-group property. Okay, so this is all that I will say about it, but if you're curious, you can read up more about this. Of course, all of this, I mean, not this particular part, you will not find this in Nielsen and Chuang probably, but you can read up about dynamical semi-groups. I'm sure there are enough references out there that you can look up, but everything else I've discussed so far is all chapter 8 of Nielsen Chuang. And I think I already posted this reference on Moodle also. Okay, so this is just to tell you how this time aspect works, right? And having told you about time and shown some examples with single qubit maps and all that, I will no longer talk about time for maybe the rest of the course, okay? We will just assume that there is an initial state and there is a final state, and the final state happened by the action of such a map on the initial state. So we will get back to this abstract picture and we will hide this dependence on time in the noise parameter, right, for the rest of the course. Okay, so the next topic that I wanted to discuss today is this idea of freedom in Krauss representation. And this will turn out to be very useful when we try to do error correction. So this is something we already observed, okay? And you may not remember, but maybe 2 weeks ago when we discussed this Choi state and things like that, where we extended it to a larger Hilbert space and all of that, we saw that it is possible to have multiple decompositions of this Choi state in the larger space, right? And so we already noted that the Krauss representation, you know, where I associate some set of operators EI with the quantum channel E, is not unique. Now this might seem like a bit of a problem, because now in the last couple of lectures, we have basically said that these Krauss operators are the noise operators, right? So now if you're telling me that this is not unique, then how do I hope to correct for this noise? Because I'm characterizing the noise in terms of these discrete set of operators, in terms of, you know, because this abstract map I cannot deal with. But I would like to break it down in this operator sum representation, and I'd like to talk about, okay, there's an X error, or there's a Z error, or there is a E0 error, or an E1 error, and so on, right? So these are the noise operators, but now what I'm saying is that they are not unique. So first of all, let's observe this using a couple of examples, this non-uniqueness, okay, and the two simple examples you can do. So the first is you can just take the phase flip channel itself, a symmetric kind of phase flip channel. So let me say there's a channel E with two Krauss operators I over square root 2 and sigma z over square root 2. So I'll just call it z over square root 2. Okay. So now think of another channel F which has Krauss operators, projection on 0 and projection on 1. Okay. And the claim is that both of these actually represent the same channel. So is it possible to show that? So it's possible to show that if you notice, so let me call this as E1 and E2, and let me call these two Krauss operators as F1 and F2. So the claim is that they represent the same quantum channel. So what do you notice about these Krauss operators? F1, F2, E1, E2, can they be related in some way? Can we relate these four Krauss operators in some way?
I plus minus z by 2 is 0, 0 and then 1, 1.
I plus minus z by 2 or root 2? 2, you're saying, okay. Okay, so good. So what you're saying is that you can represent one set of Krauss operators as linear combinations of the other. So I would prefer to do this, where I'll say E1 is I by root 2 is nothing but F1 plus F2 by root 2. Is that right? And E2 is F1 minus F2 by root 2. So of course I can invert these two. So this is nothing but, so this is a linear relation between the two sets of operators, right? So similarly, I can say F1 is E1 plus E2 by root 2 and F2 is E1 minus E2 by root 2. So once you observe this, now you see E acting on some rho, which is, yeah, you can do it either way. So let me do it this way. So E1 rho E1 dagger plus E2 rho E2 dagger. So I simply now replace the E's in terms of the F's, right? And then I will notice that this gives me the same as F acting on rho. So let's just do that. So this is half F1 rho F1 dagger plus F1 rho, F2 rho F1 dagger. So maybe I'll just do this in 2 steps because I need you to observe that there are cross terms, okay? So there is now F1 plus F2 rho F1 dagger plus F2 dagger, right? None of these are Hermitian or anything. Well, okay, the first set is Hermitian, the second one is not. F1 minus F2 rho F1 dagger minus F2 dagger, right? That's what this is. So now you notice that if you just had one of these terms, then you will have cross terms here, right? So you will have F2 rho F1 dagger and F1 rho F2 dagger and terms like that. And these should not occur in a Krauss representation, okay? So the key point is that, of course, these will get cancelled now when you expand the second term. So you will again have another F1 rho F2 dagger, but then all the cross terms will now come with a minus sign, right? So this is a very simple example. So you see that these cross terms go away because of the minus sign, and of course you end up with F1 rho F1 dagger plus F2 rho F2 dagger, and this is nothing but the way you would do the operator sum expansion for the map F, right? So this tells you that the map E and the map F are exactly the same, although they were described by two different sets of Krauss operators. But the key point was that there was a linear relation between the Krauss operators of the first representation and the Krauss operators of the second representation, right? So it is possible to have multiple Krauss representations for the same channel. And what do I mean by the same channel? The action on any density operator should be the same. The action of E on rho should be the same as the action of F on rho, and that is when I would say that these two maps or these two channels are the same. So the Krauss representation, therefore, is not the be-all and the end-all of a map, right? It is just one way for us to understand the action of the map. It's a very useful tool, and that's what we will use throughout, but one should understand that because of this, it is not unique, right? So in general, when you try to prove results in error correction or theorems or, try to understand things, you should not have things which depend on the Krauss representation, right? Because that is just one way to understand the map, right? What really is the, describes the action of the map is this action on the channel, action on a density matrix, action on a state. Okay, just one second example, and this I will leave you to work out. Okay. Of course, there were a couple of more examples, actually maybe two more examples. So we already saw this example with the depolarizing channel. But okay, maybe I will, that we didn't have quite a Krauss representation for the second time. So let me instead focus on the phase flip channel. Okay. The phase flip channel, remember, had these two, it had square root 1 minus p identity and square root pz, right? It turns out that there is an equivalent representation in terms of two operators, which I will call, again, I will call them E0, E1, okay, where E0 is 1, 0, 0, square root 1 minus lambda. Let's see if I can get this right. Yeah. And E1 is 0, 0, 0, square root lambda. Now, this is very interesting. You see, you have a representation of this in a way which is similar to the amplitude damping representation, right? So this is now homework for you to prove that your phase flip channel, I think I just call this as E sub P, right, is equally well represented by these two Krauss operators, right? That this gives you the same as 1 minus p rho plus p z rho z dagger. Of course, the key to showing this is to relate lambda and p, right? So you can take it from me that these two channels are the same, and then find the relation between lambda and p, and then use that relation to do the converse way, right? So maybe do this exercise this way, that you show that, I mean, you assume that these two are equal, that these two representations give you the same channel, and then relate lambda and p. Okay. So this is a completely different way of looking at the phase flip channel. And this is the reason that phase flip is also often called phase damping. Okay, because there is a very similar idea like amplitude damping, that you have this term which is damping the one, and then but then you have you don't have an off diagonal term, rather you have a diagonal square root lambda term. But that's why this channel is also called a phase damping channel. And the challenge for you is to now find the relation for me between lambda and p so that these two channels are the same. Okay. So what I want to do in the remaining time today is to understand whether this is completely arbitrary, like can I simply keep pulling operators out of my hat and getting Krauss representations for a channel, or is there a method to this? And of course, the answer is there is a method to this. The decomposition is not unique. And in fact, two representations corresponding to the same channel are related in a particular way. So that's the theorem proof I want to do. So two sets of Krauss representations, let's say I going from 1 to n, and another set F, we call this J going from 1 to some capital M. I mean, in all these cases, I've made it simple. They're just two Krauss operators in each representation. You don't even have to have the same number of Krauss operators in the two representations. So they are both Krauss operators or Krauss representations of the same channel E if and only if they are related as EI is some set of linear coefficients times Fj. Okay, this much we already know from the example that they have to be linearly related, but these are not any coefficients. There's a reason that I wrote this as Uij. Uij are entries of a unitary matrix. Now the unitary matrix, so J here goes from 1 to M, right? And this is true for all I going from 1 to N, right? So these Uij should be entries of a unitary matrix, which could either be M cross M or N cross N, depending on which is larger. So if M is greater than N, then there should be an M cross N. And if N is greater than M, then it should be an N cross N. Of course, if the two representations have the same number of operators, then job is simple. It's just a N cross N unitary matrix. Okay. Now, this one can again understand in two ways from a physical perspective, and one can prove this, of course, mathematically, which also we will do. But it is useful to understand the physical origin of this freedom, right? So I think I already discussed some of this in previous lectures. So where does this freedom come from? The fact that you can have multiple representations and they are related by coefficients which are drawn from the entries of a unitary matrix. So where does this freedom come? Yeah,
I think from the possibility of multiple bases.
exactly. Good. Yeah. So that's, yeah, we mentioned this maybe 2-3 weeks ago. So it's good that people have been paying attention. So the physical origin of this is basically the fact that you have a choice of basis for the environment system. So if you think about this picture where you had this unitary, which was the system bath unitary, and then you had the system state, and then you had this environment. And remember, we said that you start with some fixed state of the environment and stuff like that. Now, what one is saying is that you could have applied some local unitary, and let me call this local unitary as V. Let me call this as some V sub E. Okay. So the idea is that one could have applied a local unitary here, right? Okay, actually not here. I'm sorry. So I want to apply, I want to put a sequence. Okay, so let me say that the environment started out in a fixed state. And then the way we get this is we said by tracing out the environment, right? So I want to put a local unitary here, okay, before I do this tracing out. And I can always do that. One way to understand this is basically what you're trying to fix is the measurement basis in the environment. So it's as if you're trying to say that you're changing the measurement basis in the environment system. Why do I call it a measurement? Because effectively what you're doing with this tracing out of the environment is as if you have done a measurement in the environment, but you don't know the outcome. How will you represent the state? The post-measurement state will be represented as a sort of convex sum of all the different possible outcomes, right? And that is what happens here. You end up with a map on the system, which is a sum of different Krauss operators. So this is what we would call a local unitary on the environment system. And one is always allowed to do this without affecting what happened to. So if I had put this here, that would be different, because after that comes a unitary which is correlating system and environment. So this would not leave the map unchanged. But as far as the action on the system state is concerned, the action has already happened by this time. So after this, I can apply any random unitary in the environment system and not affect what the physical map or the action of the map on the system is. I will not affect the system dynamics by doing this, right? So this is just a circuit picture to show that I have a unitary freedom in the environment Hilbert space, and it is this freedom which is getting reflected via these coefficients here. So one can actually do a simple calculation to show this. So let's say that I have the Krauss operators EI, right? They come from this, right? Where, so if you remember the system environment picture, then we said that these Krauss operators essentially come like this. So let's say that I started with the state E0 here, okay? Then if you remember, we were doing a partial trace over the environment, etc. This is how we got to the operator sum representation, right? So let's recall this from previous lectures. Now I want to show that there exists another Krauss representation in terms of the F operators, right? Where I claim that this is now arising because I, over and above this joint system path unitary, I now have an identity tensor VE, right? There's nothing happening on system. That's just an identity gate. Tensor, because it's now independent. Right? I'm doing a local unitary only on the environment. So VE. And now if I take the same, if I do the same sort of tracing out of the environment, right? I get a different set Krauss representation Fk, but the claim is that this Fk is now related to the EI in the way that I stated in this theorem, right? So if I do this, I should get back this theorem, and then by this theorem, both EI and Fk, I mean the E's and the F's will represent the same quantum channel, right? So this you can see basically by introducing another identity here. So you introduce an identity system tensor identity environment, okay? And this this identity on system does nothing here. So what we will do is this identity of the environment we will expand in the same basis, right? You have this basis completeness relation. I can expand identity in terms of the same basis, right? Projections on the same basis. And then you see that, okay, let me call this J. So I have a sum over J, EI, VE. Actually, no, I wanted this to be EK, right? Sorry. So let me make this K, and then this can just be I. So this is V. I'm sorry that my U's and V's look similar. So there's a K, sum over I, EI. And then I have EI, the joint unitary, right? This gives me the original Krauss operator. This part, let me write it properly, I'm sorry. This is EK VEEI, right? This is an operator in the environment space itself. These are vectors, basis vectors of the environment itself. So this is what I call little UKI, right? So this is a unitary. And so these are now elements of a unitary matrix. They are entries of a unitary matrix, not any unitary matrix. They are now entries of the unitary matrix VE, which we use to rotate the environment to a different basis, right? So sum over I, EI. And what are we describing here? FK, right? So this is what is stated in the theorem, that two different Krauss representations must be related by coefficients which are elements of a unitary matrix. And in this case, this unitary matrix essentially has the same dimension as the environment, right? So if the environment is D cross D, then, I mean, if the environment is D-dimensional, then this is a D cross D matrix. So this has the same dimension, or rather its dimension is dictated by the dimension of E, the environment. Okay, so this is one way to understand where this unitary freedom in Krauss representation is coming from. And we can prove this mathematically very easily. So let's now prove this. So proof of this unitary freedom. So the easy direction to prove is, of course, this, that if I have two sets like this, let me stick to the notation that I used here, which is EI. So if I have EI being equal to sum over J Uij Fj, I think that's what I wrote down here. Okay. Then you can see that E of rho is sum over I EI rho EI dagger. So you replace all the EIs with this, then now you will have sum over I, you will have sum over J Uij Fj rho, sum over K Uik star Fk dagger. So now, of course, you'll pull the J and the K sums outside and take the I sum inside. So what you will have is sum over I Uij Uik star, right? And then Fj rho Fk dagger. And now this, what happens? What is sum over I Uij Uik star? So of course I should mention here that these are entries of a unitary matrix. This is one direction of this. So yeah, I guess you all know that this should be delta JK, right? Because of the unitarity property. So then this simply becomes sum over K Fk rho Fk dagger, which indeed is a Krauss representation for the map F with Krauss operators F. So I mean, I didn't call it two different things, but anyway, this proves that both of these are Krauss representations for the same map E of rho. So if I have two sets which are related like this, using coefficients which are drawn from a unitary matrix, then the two operator sum decompositions represent the same map. Now we need to prove the other way around, which is that if I have two sets of, I mean, the claim should now be that if E of rho is such that it is sum over I EI rho EI dagger is the same as sum over k, fk rho, fk dagger, then these two must be related via coefficients which are drawn from a unitary matrix, right? That is what we need to show next, right? So how do we prove that? To do this, we go back to the Choi state. I don't know if you people still remember what the Choi state was. So let us start here. So let us say that we are given that there exist two sets of Krauss representations for the same map. Now recall the idea of a Choi state, which is basically that, yes, can anyone remember what the Choi state associated with the map is? So I call this some sigma RE, which is basically identity map acting on R, tensor the map acting on, okay, I don't want to say E, I'm going to say S, sorry, acting on the system. And this tensor product map is now acting on a maximally entangled state of the reference and the system. 1 to D, let's say. So let's say that you have your system Hilbert space, you have a reference, right? And both of these are D-dimensional. Okay, this is the context. And then you extend the map with identity on the reference and you act it on a maximally entangled state of this form of the reference and the system. This is the Choi state. So now where does this unitary freedom come from? Remember that this is a density matrix on R tensor S. And now recall something we did last semester, which is that there exist multiple ways to decompose a density matrix into pure states, right? So you have a unitary freedom in decomposing this density matrix in terms of pure states. So there is no unique pure state decomposition for a density matrix, and the freedom in Krauss representation can now be thought of as coming from that mathematical property that there are multiple pure state decompositions for the same density matrix. So if you don't recall this, please go back to chapter 2 of Nielsen-Chuang where we did this. I think this was called the Houston-Joseph Wouters Schrödinger theorem, right? And we did spend some time proving this and understanding this. So please go back and look up this unitary freedom. So what does it say? So it says that given a density matrix rho, suppose there is one pure state decomposition like this in terms of states psi and the probabilities pi, and if there is another pure state decomposition in terms of states phi and probabilities qj, then this is true if and only if the states psi and phi are related in a similar fashion, right? That there exists some unitary matrix whose coefficients form this superposition, and this in this case has to do with the weighted states. It is not just psi I is related to phi j in some way, it's that square root pi psi I is related to square root qj phi j, where these probabilities also show up in this linear relation, right? Where this comes from a unitary matrix. I hope you all remember this statement. At least now that I mention it, I hope you recall it. One special expansion like this is, of course, the diagonal representation of the density matrix, but that is just one representation, right? It has multiple pure state representations and they're all related like this. So we simply have to apply this now to this Choi state of the map. Okay, so now let us do this. So define, so you recall this, okay, and now define So we basically have to define two sets of pure states. Okay. We'll call this as EK. So this is one set of states in, now this is a joint system, right? HR tensor HS, and another set of pure states, which we will call FJ, also belonging to this composite Hilbert space, right? So now I want to define these such that sigma RS is sum over K EK EK. So these are now unnormalized. Okay. So these are both not normalized sets. But now we can go back and relate these to the map E, and we can relate it to two different decompositions of the map E in the following way. So you have the choice state. This has two different decompositions. So I can now define the state E, the set EK as coming from the action of the set of Kraus operators E, the E set of Kraus operators. So it's identity in R tensor this acting on this maximally state. And I have the other set of states coming from the F representation. Right? So if you recall how we defined the EI now in the earlier case. So, I mean, this is just to say that, okay, so if I define this EK is a pure state decomposition for this choice state, and I define FJ to be another pure state decomposition for the choice state, then that automatically implies this in some sense. Because if I have to represent, so if you remember what the choice state is, it looks like this, right? Identity tensor the map acting on this maximally mixed state. So this is nothing but identity tensor sum over I, EI, this EI dagger, right? So if I now break it up like this, then because this is all pure states, I mean, these are now pure states sitting here, so I can sort of break it down like this effectively, right? So this EK will act here and its identity is acting here, all right? I put K here, okay? So just keep this in mind, that is where this is coming from. So what remains to be done is to show that this EK and the FJ are related according to what the statement of the theorem says. So we started by saying that there are two representations and they both represent the same map. If they both represent the same map, they must both correspond to the same choice state, right? And the same choice state can therefore be realized in terms of two different pure state decompositions. But then we know that these pure state decompositions must be related via a unitary transformation. So let me just give a sequence of arguments. If this is 1, then 1 implies that the E states and the F states must be related via this unitary, via a set of unitary coefficients, right? And now if you go back to what that implies for the Kraus operators, then again recall that the way you get the Kraus operators is that EI acting on psi is psi tilde acting on EI, and psi tilde is a state only of the reference. This is all system, and EI is a state of reference and system. So this was all from last week, so please, or 2 weeks back. So please go back and look up how we got the Kraus representation from the choice state, and then you will see this. So all that remains is to just plug this in here, that this EI is related to the FJ like this, and everything being linear out here, this becomes sum over j uij psi tilde fj. But psi tilde fj is associated with the other Krauss representation, right? So this is uij fj. And so this sort of shows that this is true for all psi. And so this shows that the EIs must be related to the FJs like this. And this is for all I, etc. Okay, so that completes the proof. I don't know how many of you are still here and how many of you followed this. But if you have questions, I can answer them. No questions? Okay. Let me just go through this argument again. The first part is clear that if two sets of Krauss operators are related like this, they must correspond to the same map, because you simply do the operator sum decomposition and you show that you get the same map, right? Now the converse is, if two sets of Krauss operators represent the same channel, the same map, then they must be related to each other as described there, right? And to do that, the first step is to say that they correspond to the same Choi state, okay? And then that Choi state, which is sigma RS, can be written in two equivalent ways, pure state decompositions. And those two pure state decompositions must be related via a unitary transformation like this. Once you do this, then all that remains is to write down the Krauss operator from the Choi state. And how do you do that? You do that via the pure state decomposition of the Choi state. If you remember, that's what we did 2 weeks back. You take one pure state decomposition, you get one Krauss representation. You take the other pure state decomposition, the F1, and you get the second Krauss decomposition, which is the F. And these two are related by this unitary. That comes from the fact that if two density matrices are related, have two different pure state decompositions, then those must be related by a unitary, right, which is this. Okay, so that concludes this argument. One final observation that I want to make, and I will probably stop with this today because I don't want to start something new after this. The final observation that I wanted to make is, because of this unitary freedom in Krauss representation, one can actually then talk about what is a minimal description of a map, right? So an interesting corollary of this is that to describe a quantum channel on a d-dimensional Hilbert space, all one needs is d squared Krauss operators. So this is the corollary, that all quantum operations on a d-dimensional Hilbert space can be generated by a Krauss decomposition with at most d squared elements. What this means is, physically you may want to describe the map using as many ever Krauss operators as you want. But if rho belongs to a d-dimensional Hilbert space, right, then I can always find one Krauss representation which has d squared elements, and this is a kind of bound on how many I need to describe any Krauss, any quantum channel. So I never should need more than d squared Krauss operators to describe a quantum channel. Okay, so what this means is, for example, for qubit channels, we need at most 4 Krauss operators, and that will describe. So if I want to write down the most general possible qubit quantum channel, then I'll have to write down 4 Krauss operators to describe such a map. So far, all the maps we've discussed have had only 2 Krauss operators, right? Whether it's, well, I'm sorry, except for the depolarizing, of course, where we used all 4. And that should also tell you where this number d squared is coming from. If you look at the depolarizing channel, the 4 operators which constituted the Krauss representation were all independent, linearly independent operators. They formed the basis for the space of operators. Similarly, for any d-dimensional space, you can think of an operator basis, and that will then tell you that you don't need more than d squared elements, d squared Krauss operators to describe a quantum channel on a d-dimensional space. Okay, so this I will stop here today, and next week onwards we start discussing error correction. Questions?
No, ma'am.
Yeah. Was there a question?
No, I was saying no questions.
Okay, okay. Fine. So I'll see you all on Monday next, and probably next Tuesday I will post another tutorial to cover some of what we did this week and next week. Okay. See you all then.